Hello everyone, in this video we will be covering section 4.5, which is called base rule. Before we do base rule, you need to apply something called the total law of probability, and the total law of probability depends 100% on section 4.3, which was the conditional probability formula. So this is what the total law of probability says. The probability that A is going to happen is the same thing as the probability that A happens and another event happens, or, and this will be mutually exclusive, the probability that A happens and the second event doesn't happen. If we expand this formula, this one, using the conditional probability formula from section 4.3, which was this, okay, you will end up with this. You use the little algebra. This is the probability that B happens, then the probability that A happens given that B already happened, and so forth. It will be the probability that B didn't happen, that's the probability that A will happen given that B didn't happen. So this is not base rule, this is the total law of probability. So we need to do this before you apply base rule. Base rule is actually just this formula, you will see, but you cannot do base rule without having done this part first. That's why it has a different name. Now here are the good news. You don't actually have to worry about this formula at all. All you have to do is a tree diagram, and then it will be very easy to solve the problem. So we're gonna still use the formula, but we're not going to write the formula explicitly. So you'll see what I mean right now. This is what I mean. Suppose that 40% of the population is vegetarian. So the person is either vegetarian or the person is not. So this is telling you that 40% is vegetarian. That implies that 60% is not. Now, if the person is vegetarian, they either have a computer or they don't have one. Same thing for the non-vegetarian people. This is telling you that if the person is vegetarian, that there is a 90% chance that they have a computer, so therefore there is a 10% chance that they don't have one. Then it tells you that is 80% chance of this side, so hence there is 20% of this side. Now this is how you're going to do the problem without really using the formula. The question is asking you what's the probability that the person doesn't have a computer. Well, there are two ways to get to no computer. Either the person is vegetarian and he doesn't have a computer, or the person is not vegetarian and he doesn't have a computer. And these two events are mutually exclusive, so they cannot happen at the same time. So all you have to do is add the probabilities. So therefore this will be equals to 0.4 times 0.1. So all you have to do is follow the tree. 0.4 times 0.1 plus 0.6 times 0.2, which will give you 0.04 plus 0.12, and then this is equals to 0.16, and that's it. So you can see this pretty easy, and you don't have to bother at all with this formula. Now for part B, you can do exactly the same thing. Follow the tree this way now, or there is an easier way. The probability that somebody has a computer, it will be equals to 1 minus the probability that the person doesn't have a computer, because these two events are the complement of each other. So then all you have to do is use the result from part 8. So it will be 1 minus 0.16 which is equals to 0.84. That's it. Okay, so now let's actually do Bayes' rule. This is the part that is Bayes' rule, and like you see right now, this is nothing more than the same formula from section 4.3, but you cannot do this without having done all of this first. That's why it has a different name. Okay, so now remember that if also means given. So this is what the question is saying. Given that the person owns a computer, what is the probability that the person was vegetarian? Recall that this one always goes on the bottom, so this will be computer, and on the top it will be vegetarian and computer. The answer to this one is part B, which was 0.84, and then on the top it says the person is vegetarian and owns a computer, so it will be this times that. So this will be 0.4 times 0.9, which gives you 0.42a, and this rounds to 0.43, and that's it. Regardless of how the question looks or the question is asking, the best way to do these problems, and the easiest one, is to do a tree diagram like this. The next question is asking something completely different, but we're gonna do exactly the same technique. Let's do another example. Here it says, suppose that 3% of the population has a rare disease. So the first brand should be this. The person either has a disease or they don't have it. And there is a 3% chance that they will have it. So therefore, that means that there is a 97% chance that they don't have it. Now, if the person has a disease, when they take the test will be either positive or it will be negative. Same thing if the person doesn't have the disease. This is telling you that if the person has a disease, okay, the test is 98% effective, which means 98% of the time the test will be positive and 2% it will be negative. The part we have to be careful is this. The question says that the test is 97% effective if the person does not have the disease. If the person does not have the disease, effective means that the test has to be negative. So therefore, this will be 0.97 and this will be 0.03. Now, in case you haven't noticed, the branches always have to add to 1. So you can see this is 1, 1, and 1. Once you have done this is very easy to answer the question. The question is asking what's the probability that the test is positive. Well, just like the last problem, there are two ways to get to positive: disease and positive, or no disease and positive. So therefore, the probability that the person will test positive is 0.03 times 0.98 plus 0.97 times 0.03, which is equals to 0.0585, or around 0.06. And that's it. Now, the probability that the test will be negative, we can do the same trick within the last problem. Just use the complement. The complement of negative is going to be positive, so this will be 1 minus 0.06, which is around 0.94. All right, let's do the last part, and this is the actual Bayes rule. This is what the question is asking. It says, if the test is positive, so now you already know this, that the test was positive, what's the probability that the person actually has the disease? So then follow the conditional formula. Remember, this goes on the bottom, so the bottom will be positive. The top will be disease and positive. So positive, remember, was 0.06, so this will be 0.06, and the C's was 0.03, positive was 0.98, this is equals to 0.49, which rounds to 0.50. That's it. I told you this was pretty simple.